Welcome to Energy Talks, a regular podcast series with expert discussions on power system testing topics. My name is Scott Williams from the podcast team at Omicron, and I will be your host. Current transformers used for metering purposes in medium voltage power systems must have a high accuracy from class 0.5 up to class 0.1 to ensure accurate billing. In this episode, we will discuss how current transformers, also known as CTs, are used in the metering process, why their accuracy is so important, what causes errors, and how this can lead to billing losses. In addition, we will find out how and when instrument transformer testing plays an important role in assuring the required accuracy. Joining me to offer his insights into this topic is Roland Berga. He is a business development engineer at the current sensor company SENSELEQ. Roland is based in Germany, and he has a lot of knowledge about and practical experience with current transformers used for energy metering. Hello, Roland. Welcome to Energy Talks.
Hi, Scott. Nice to be part of this podcast.
Also with me is Felix Feustel. He is the product manager for instrument transformer testing at Omicron. Hello, Felix.
Hello, Scott. It's great to be here.
Thank you both for joining me. Roland, I'm going to start with you. Could you please tell us about SENSELEQ? What types of sensors does your company produce, and who are its customers?
Yes, SENSELEQ offers resin-casted zero-flux sensors which can be used on transformer bushings. These sensors are very accurate. The amplitude error is under 0.05%. In addition, these sensors can measure a DC component. That's why they cannot be influenced in the accuracy by remnants effects due to faults in AC systems or geomagnetically induced currents. Our customers are using these sensors for power quality measurements and for reference measurements.
Interesting. So, Roland, what is your role in the company, and how have you been involved with current transformers and energy metering?
Yeah, at SENSELEQ, I'm working as an engineer in the business development. In the last 14 years, I was working for two traditional instrument transformer manufacturers. Here we have calculated a lot of metering CTs, which have been connected to the billing meters.
Okay. How are current transformers used in the metering process?
Yeah, in Germany and a lot of other countries, inductive current transformers are the only certified devices which can be used for measuring currents which cannot be handled directly by the meter.
Why is their accuracy so important for the metering process?
Yeah, the accuracy affects the financial amount of the measured kilowatt hours. Let's take an example. In a 20 kV system, there's a rated current of 600 amps. The kilowatt hour costs, let's say, 20 euro cent. If the voltage and the current transformers have only an amplitude error of 0.1%, which is very accurate, we generate a difference in the financial amount of approximately 1.5 million euros in 20 years.
Wow.
And in this example, we do not have taken the phase displacement into account. Moreover, in many cases, an amplitude error of 0.5% is still okay for the authorities.
Okay, very good. Well, Roland, you work with customers in Germany. Are metering practices in Germany different than in other regions of the world?
Yeah, in some areas of the world, the utilities are able to use alternative sensor technology, but in many countries, the metering practices are nearly the same like in Germany.
Okay. Could you please explain why metering current transformers in general produces an error during current transformation?
Yeah, the current transformer is an electrical transformer. So you need a magnetization current for the iron core, and you have some losses in the copper winding. But the most important thing is that the end user can influence the amplitude error and the phase displacement by changing the burden impedance, which is connected to the output terminals.
Okay. Could you please explain how this works?
Yeah, the rated output on the rating plate of a CT is tested by the manufacturer with 25 and 100%. And if your burden power is in this range, you can be sure that you are in the specified accuracy class. In general, if you are at 25% of the rated output, the amplitude error tends to be positive. And if you are at 100% of the rated output, the amplitude error tends to be negative. As a result, with a smaller burden, you can measure more current than is actually flowing through the bus bar. By comparison, with relative big burdens, you are measuring less current.
Roland, what is the relation between the accuracy class and the percentage amplitude error of the current transformer for different primary currents?
The admissible operating parameters are given in IEC standard 61869-2. They list up, for example, the limit values for amplitude and phase errors for metering transformers with different accuracy classes. Current transformers for billing measurements require at least class 0.5 in medium voltage and low voltage applications. The name of the accuracy class corresponds with the percentage amplitude error at the rated current. If the amplitude of the rated primary current is under 20%, the tolerated error is higher for the classes 0.5 and 0.2. Here, the standard takes the non-linearity of the magnetization curve into account.
Roland, how does an operator know which rated power to select?
When selecting the rated power, the measuring point operator is bound to the rated power standardized by organizations such as the PTB in Germany. The real burden in the field, which consists of the resistance of the meter and the cabling, must be in the range of 25 and 100% of the rated burden. This burden can be measured, or you can calculate the value if the meter manufacturer has specified the right resistance of the input channels.
Okay. Roland, just to clarify, you mentioned the PTB in Germany. What is the PTB?
Yeah, the PTB is the National Metrology Institute of Germany with scientific and technical service tasks. It is a federal authority and a public law institution directly under federal government control.
Roland, do other limit values for test burdens also exist?
Yes, the value 1 VA was set as the smallest test burden for billing current transformers. So if there are values like 1 or 1.5 VA on the rating plate as rated output, the CTs are only tested with 1 VA as the minimum value. It should also be noted that the power factor for all measuring points is 1.0, below 5 VA. All powers from 5 VA and above are measured with a power factor of 0.8. These measuring points must be in the class specified on the rating plate.
Very good. Do all end users choose the right rated output for their CTs?
Yeah, actually, I do not have any statistics, but we have seen in the past that many current transformers have been loaded only with very small burdens because a lot of meters have only 2 to 100 milli VA. As mentioned before, you measure more current than is flowing through the primary cable. In this case, you can increase the financial amount. In some cases, the devices were also overloaded due to long connection cables.
Roland, why are the deviations in the invoice amount caused by billing current transformers in the high voltage grid even higher than in an environment with lower currents and voltages?
Yes, Scott, this is a good point. The electrical power is calculated by voltage multiplies with current. So if you have higher voltages, the deviations can increase significantly. That's why a lot of current transformers in high voltage systems are very accurate. They fulfill class 0.1 or 0.2S.
Are there any similarities between voltage transformers and current transformers?
Yes, like current transformers, the voltage transformers required in medium voltage must meet the accuracy classes defined in the IEC standards as well. There are also standard burdens specified by the PTB in Germany. For the voltage transformers, there's a unique phenomenon. In addition to the external supply of the digital meter, the meter can be supplied with the necessary energy via the voltage pass. This creates further problems. This is because the energy meters are usually operated with different communication interfaces, especially in the medium voltage range. Here, outputs of up to 10 VA can be called up by the voltage transformer. This is probably the reason why new medium voltage standards for utilities in Germany specify voltage transformers with 15 VA in class 0.5. However, communication units such as GPRS or LTE radio modules only send the data to the corresponding server in certain time windows. The power requirement of the counting device can therefore be described as fluctuating strongly. Typical values are between 0.1 and 10 VA. So if we have a rainy day, the LTE module needs more time to build up a wireless connection to the antenna. In this case, the voltage transformer is loaded with, let's say, 10 or 15 VA. As for the current transformer with a bigger load, you get a negative percentage error. As a result, the utility will earn less money when you have bad weather.
That's very interesting. Roland, how would you summarize the most important preparations a measuring point operator should take?
Yeah, it is important for the measuring point operator to have the correct burden for the instrument transformers. In addition, sometimes you can find the best burden for the instrument transformer to achieve the highest accuracy. Therefore, you need CT test devices which can generate an electrical equivalent circuit diagram. Moreover, you can use zero flux CTs above 110 kV, which are more accurate than normal CTs.
Roland, thank you very much for sharing your practical experiences and knowledge of this topic. Very much appreciated. Felix, I have some concluding questions for you. First, could you please describe how Omicron is involved in instrument transformer testing, and what is your role in this area of testing?
Yes, gladly. Well, Omicron has a whole range of test devices that relate to the testing of electrical or insulation performance of instrument transformers. Firstly, there's a kind of multifunctional direct measurement devices for the electrical performance. And then also I would say that Omicron is the leader in model-based testing and calibration of both current and voltage transformers. And also to be mentioned is a range of test devices that relate to the insulation performance, such as tangent delta or partial discharge measurement devices.
Mm-hmm.
And as the product manager, I have been involved with several of those products. And in the last time, I would say I was mostly focused on conventional electrical test devices, and in particular the model-based ones.
Felix, how can the impact of the burden on the accuracy of current transformers be tested?
A good approach here is to use a model-based test set, because this measures the parameters of the current transformers according to the equivalent circuit diagram. So it means that, for instance, the copper losses are described as the winding resistance of the current transformers. And similarly, there's a modeling of iron losses, which are broken down into eddy losses and hysteresis losses to have the characteristics of the core. And then based on a whole range of measurements to feed this model, the calculation of the current transformer transformation error and phase error for any specified current or any burden value is performed.
How does one know if the current transformer fulfills all accuracy class requirements for a specific burden?
Well, when we have the knowledge about the total losses of the CT, our device is able to calculate the current ratio error and phase displacement for any primary current and for any secondary burden. And therefore, all operating points which are described in the standards for current transformers, similarly to voltage transformers, can be ascertained. And the device automatically determines all relevant current transformer values and then directly compares those results with the selected standard. It then gives an automated assessment based on the standard rules.
Felix, are there any other advantages of this approach?
Yes. Firstly, in the same measurement sequence, other essential quantities, for example, the ALF or FS factors, the dimensioning factor KTD, or the knee point voltage can be determined without rewiring. Additionally, important parameters such as the residual remanence can be measured on the same occasion. And then the accuracy performance of the current transformer, as it can be calculated and re-evaluated quite easily, even on site, we can even envision that in the future, the real operating burden, as it is present on site, including wiring impedance of the energy meter, and also the wiring resistance of each particular instrument transformer, can be measured during the commissioning in the substation. And then the specific amplitude and phase error for any given current transformer can be calculated for such a setup. If then the energy meter supports the compensation of current and voltage transformer errors, there can be achieved a much better overall accuracy than just relying on the boundaries of the accuracy classes and the rated burdens.
How often should this testing be performed to ensure accuracy requirements? And Felix, what action should be taken if discrepancies are found?
I would say the most important thing is to test at all, to perform tests at all. Ideally, the current transformer ratings should be verified at the factory and then compared with a model-based test set. And after that, this model-based test set can then be used for commissioning and recommissioning tests in the substation, as well as for periodical recalibration, if desired. I would say if we find a discrepancy, we have the possibility to take a closer look where does discrepancy come from. Is it a characteristic of the current transformer itself, or is it maybe due to an over or underburdening? In those situations, we can then take the appropriate actions, like either checking back with the manufacturer of the device, or on the other hand, adjusting the burden to bring the transformer into an operating point where it performs optimally and has a minimum amount of error.
Felix, where can our listeners get more information about instrument transformer testing at Omicron?
My recommendation is always to sign up at the Omicron customer area. This is a free of charge platform, and there, among many other things, there's a large selection of technical papers and articles, for instance, from the various events that Omicron has hosted or participated in over the years.
Okay, but you have to be a customer to do that, right?
No, not really. Anybody can sign up.
Interesting. Okay. And also there's information about instrument transformer testing under applications on our website.
That's right.
And Felix, what about Omicron Academy courses? Are there any online courses or webinars on this particular topic?
Yes, sure. The Omicron Academy covers most or almost all of the assets in the substation, and we also have a dedicated track about instrument transformer testing.
Roland and Felix, thank you both very much for sharing your insights into this topic.
Thank you, Scott. It was a pleasure.
Thanks, Scott. It was nice to be here.
Thanks again. And a big thank you to our audience for listening to this episode of Energy Talks. We always welcome your questions and feedback. Simply send us an email to podcast@omicronenergy.com. Omicron has several years of experience in power system testing, including instrument transformer testing, and it offers you the matching solution for your application. For more information, be sure to visit our website at omicronenergy.com. Please join us to listen to the next episode of Energy Talks. Goodbye for now, everyone.